we came to this conclusion. If you have the linear system x dot equal to ax with some initial condition, then assume the case in which the matrix A has n independent eigenvectors. And the solution has this structure. It is a sum of terms. Each term is made of a coefficient that depends on the initial conditions. Then the exponential of an eigenvalue times time, and the corresponding eigenvector. So you multiply these things, k1 and the exponential are scalar, so you can do it in any order, and then you have this factor. And each of these terms is a mode, because it's the eigenvalue that you are considering that determines whether you are oscillating or not oscillating, or whether it is stable or unstable. So you call it a mode of oscillation. Okay, for me, an exponential is a particular type of oscillation. Okay, so a mode of change. Before we proceed, in the case where A does not have any independent eigenvectors, then this sum will be smaller than n, and you cannot generate all the states x. So you need to add an extra term, and these extra terms are terms like this, but multiplied by a polynomial in time. Okay, this comes from the so-called Jordan canonical form. Remember that this came from the fact that you can express A as the product of the matrix M times M is the matrix whose columns are the eigenvectors of the eigenvalues of A. And lambda is the diagonal of the eigenvalues, and M minus 1 is the inverse. Okay, so when you have n independent eigenvectors, you can write this with respect to lambda, and you are able to do a change of coordinates in which the matrix becomes diagonal. So all the states are decoupled. If this is not the case, then some states are coupled, and instead of getting a diagonal matrix, you get a so-called Jordan canonical form. This is something that we are not going to study. Okay, as I told you, in most cases you have this fact that you have n independent eigenvectors. So in this case, so your x is a sum of modes, always like this. And I think that we had a discussion where I wrote for different cases of lambda. If lambda is real, you don't have oscillations because these are exponentials. If lambda is real and negative, then this is a decreasing exponential. So in time you are decreasing. So it's asymptotically stable. If lambda is a complex number, then if the real part is negative, the real part is a real exponential multiplying the exponential of jt, j times the imaginary part times t, and this corresponds to an oscillation. Okay, so you have something. I think, well, this computation is an example, very complicated. You can follow it if you want, but let me show you one table. That I think I have here. Can you see it? Classificação da dinâmica em torno dos pontos de equilíbrio.
Yes.
Okay, so you have the position of the eigenvalues in the complex plane, and you have the phase portrait. So if you have, let's start by the end, okay? If you have two pure imaginary poles, two imaginary eigenvalues, then you have cosine plus jota sine and cosine minus jota sine, so you have pure oscillations. And in the phase portrait is made of closed curves, ellipses or circles, circumferences. It turns clockwise or counterclockwise depending on the signs of the derivative. But the important thing is that you have these closed curves that correspond to oscillations, undamped oscillations, oscilações que não amortecem. Now, if you look at the first case now, look at the first case. If instead of being in the imaginary axis, your eigenvalues are on the left plane, so you have now some real negative real part. And this negative real part corresponds to some damping because it's an exponential, a negative exponential that forces the mode to squeeze. So you have some oscillation that is damped and you spiraled to the origin. So this corresponds to an asymptotically stable system, linear system. If instead you have the eigenvalues with a positive real part, this exponential grows in time and you start spiraling away from the origin to infinity. Okay. If you have two real poles, two real and negative poles, then it's a combination of two negative exponentials, one faster than the other. So you don't oscillate. Probably you can do some turn because of the combination of the exponentials, but you don't oscillate. So what you have are curves like this. So you start here and you have just one turn. You don't oscillate. This is called a node. Okay. This instead is a focus, and the first one where you don't have any damping is a center. If the poles are real but are on the right plane, then the shape is the same as the stable node, but now you go away to infinity, so that you travel the opposite way. And if you have a negative real pole and a positive real pole, you have a saddle point. And this saddle point is such that along the eigenvalues, either you approach the origin or you go away. And outside from the eigenvalues, you do a movement which is the composition of the movements along the eigenvectors. Okay, so here, for instance, suppose that the eigenvector that defines this direction is associated to a negative eigenvalue. So you are approximating the origin. Okay. Now, what I would like to do is a problem. I mean, I don't want to do it. I want you to do it. So I have here 5 matrices and 5 phase portraits. And I want to match to say which matrix corresponds to which phase portrait. So what you have to do is to compute the eigenvalues and try to reach some conclusion. So start by computing the eigenvalues for all these 5 matrices. Meanwhile, I'm going to send you something. I forgot I had it. It's a very nice chapter on the basics of linear algebra. Okay, I will send it to you right away by email. And I suggest you to read it and study it carefully, because you have problems with basic computation in linear algebra, and this will for sure help you. Okay, so try to compute the eigenvalues of this. Try to compute the eigenvalues of these matrices, and start taking conclusions about which is which. Okay.
Okay. From the first matrix?
Just a moment. I have just sent it to you. Okay, from the first matrix.
So the matrix A, so the first matrix top left, the eigenvalues are minus 0.3 plus 1.38 I, and minus 0.3 minus 1.38 I.
So
So I'm faster in R than in MATLAB. So I like
oh, but you should do it by hand.
I should do it by hand. Okay, I did in R.
So for A1, you get what? Lambda minus 1, 2, lambda plus 0.6. Okay, so do you agree with me? So let's start with A1. So A1 is so this gives you minus 0.3 plus or minus j 0.36 minus 8 divided by 2. So 8 is clearly bigger than 0.39. So this is a square root of a negative number. So where, if I have the C-plane, where shall I place these eigenvalues?
On the left.
On the left, one here, and one here. So do this computation. I don't know. So what this corresponds to what? A1. So you have negative eigenvalues. What type of response is this? Let's look at the.
It's like a to the counterclockwise.
Which one, Kaveh?
I think to the D.
The
Right.
D. Yes, it's a D.
Yeah, to the
Okay.
D, yeah.
C is not oscillating. Okay.
Yeah.
C is not oscillating. So it's a D. So it's a damped oscillation. Now let's look at the others.
The others are real, -2 and -1.
Which one?
The A2 is real and is -2, -1.
-2 and -1. And this corresponds to what? So two negative eigenvalues.
Yes.
Two negative eigenvalues. Should be what?
C.
C. Why C?
Because they go to 0.
They are
Yeah.
stable, and C actually goes to
0.
zero. Could it be E?
But it isn't E.
Oh, I think.
It should correspond to what? What position of the eigenvalues?
Imaginary.
Yes,
Pure
okay.
imaginary, no? So
Yeah.
undamped oscillations, no real
Yes, there is,
parts to. Okay. Here you don't have any oscillation at all. It's just an exponential. Actually, two exponentials. That's why you do this type of curl here. Fazer esta voltinha. Okay. So A2 is C. Now let's look at the others. Any question?
No.
No. Let's look at the others. I think that I shall share my screen. I think it's better like that. Okay. So, oh, no. Ah, yeah. Here, no, no.
I can.
Where do I have my whiteboard? Zoom meeting controls.
But maybe I could see we could say the eigenvalues, and then we check just the plot.
Maybe.
The A3
Share, new
matrix.
shares. New share. Good Lord. Whiteboard. So A2, two negative eigenvalues, you go. Now, do we have a problem? Do we have a problem here?
What do you
in
mean
this,
we have a problem?
an ambiguity.
Yeah, because one is positive and the other is negative.
Yeah, one.
I mean, in general, okay. This one is okay. This one is okay. Now we have the other three, A3, A4, and A5. And what are the eigenvalues of A3?
1 and minus 1.
1 and minus 1. And the eigenvalues of A5?
1 and
Of-
minus 1.
1.
Yeah, one.
So we have a problem here. But this corresponds to what? This situation corresponds to what? What's the type of pattern that you...
A.
That's a saddle point, okay?
Yeah.
That's a saddle point. In this case, you need to compute the eigenvalue, the eigenvectors. Now, what about A4? A4 is plus or minus j square root of 2. So this corresponds to what?
To E.
To the one in which it was turning around. That's E. So we have to discriminate between A3 and A5. Okay, so compute the eigenvectors. And to compute the eigenvectors, okay, can I clean this thing before I clean it? Any question?
No, no.
No. So to compute the you remember how to compute the eigenvectors? Because one thing is true, you may not learn nothing more in this course, but in the end you will be able to compute eigenvalues and eigenvectors. And that will be something. When they ask you, what have you learned in that course, in that semester? How to compute eigenvalues and eigenvectors for 2x2 matrices. Let's also this, I don't need it. So I have to write, I have to remember, I have to compute lambda I minus A. Okay, this is lambda I minus A Vi equal to 0. Okay. Now, in this case, for instance, it would be lambda minus 1 and minus 1 lambda times, this is I Vi1 Vi2 equals to 0, 0. Now, when I select lambda to be an eigenvalue, both equations are linearly dependent, so they are the same equation, or they are equivalent equations. So I just use the first one. So I just say, well, it is lambda I V I1 minus Vi2 equal to 0. So, but now I have two unknowns and just one equation. So I say vi1 equals to 1. So vi2 is equal to lambda I. Okay? And if you say lambda 1 is 1, so v1 is 1, the first component I've selected, and then the second is lambda I, which is 1. If lambda 2 is minus 1, then v2 is, again, I select this to be 1, and the other one will be lambda I, which is minus 1. Okay? Now compute the other one. Compute the one for A5, which is here. Well, you have it. Who wants to write this? So I do some stop sharing. And one brave among you to show me the computation.
I can do that, but I don't know where to write. Can I use Paint?
Yeah, use the whiteboard.
Is it
I gave you
on
permission.
Zoom?
You should have permission to share your whiteboard.
Oh, okay, okay. Can you see it?
Yes.
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 But by the way, where do you see, where do we have the whiteboard? Where can we click?
When you click on share screen or something like
It
that?
appears.
Yeah.
Oh, okay. Okay, thank you.
When you
I
click
didn't know
on
that.
share screen, you have all the possibilities, and one is the whiteboard.
Oh, I see. Whiteboard. Okay, perfect.
Okay. So for A5,
So I did it separately for lambda 1 and lambda 2. And for lambda 1.
but I want to see the whole computation, not just the result
Okay. The computation of the eigenvector.
of the eigenvector.
Okay, so.
So you should write
But
first
do you want the
A minus lambda I,
Okay.
or lambda I minus a, whatever you want.
We can help you, Max.
Yes, yes.
Now I don't know where to.
So you have to start with the matrix where you have on the you have on the
Yeah.
top left lambda I plus 5 divided by 3.
So
If you want to, you will have some tools at the top. If you go to the top,
Yeah.
Okay, yeah.
you should have some tools. Are
But
you looking?
is it working
Okay.
now?
Yeah,
Yes.
yes.
yeah.
A minus lambda I, okay.
Fine.
That's really a matrix. That's not that.
Yeah.
That's a matrix.
Vi.
Yeah, equal to 0.
I suggest you to use a superindex on the top for the vector, because then the superindex has two components, and use the lower index for the components. You see? So put the I
Here?
on the top.
Yeah.
Okay. Then when you write it as component by component, component-wise, you have VI1 and VI2, and use the subindex. Okay, so this is equal to
0.
0. Okay, so now write that equation.
Now, so it's
Okay, but stupid question, but isn't it lambda I minus A?
Okay, is it a minus lambda I or lambda I minus a?
isn't it the same because we are saying
No,
that
we
it's equal
inverse the
to
signal.
0.
Yeah.
You just
we inverse
multiply
the
by
signal.
-1, no?
Yeah.
You multiply -1 on the left, and
Yeah.
on the right you get 0 again. So it's immaterial. They are equivalent.
I think the sign of minus 4 divided by 3, the above on the right is plus, and the
No, it's correct because she
It's
multiplied
writing
by
a
minus 1.
minus lambda.
So it's
okay,
correct.
okay, yeah,
She
you're right.
multiplied it by
equivalent.
-1, so it's correct.
And this is 0, 0. If you
Oh,
0
yeah.
and 0. Okay, so now which one are you going to use?
The first one.
And now?
Now, yeah, we can do it for, so maybe here. When lambda, for lambda 1 equal to 1. If we set v1 equal to 1, 2, 1 is equal to I don't know if I computed it correctly, but it's gave me -2.
So
And for-
-1 is -1 is -3 divided by 3. So that's -8 divided by 3, and then you multiply by 3 and divide by 4, that's -2.
And for lambda 2, that's 1, 2. This gave me so it's 1
-1/2. Okay.
1 is 1 -2.
Okay, so what are your conclusions? I found the solution, but I forgot what was the problem. What are your conclusions after all this
So we need
laboratory?
we need to know the direction of the vectors, and based on that, we
And
can
what are now? Okay, show us the. You want to see this? So maybe you could do a plot.
Okay.
Maybe you could do a small plot. You have some free space, yes, there.
Here, wait.
So
Can I clean this?
Yep.
Yes, yes,
Yeah.
yes.
okay.
This is really difficult. Okay, so for the first one, it is 1 -2, something like this.
So that defines that direction.
And then
Try
for the
to
other one,
plot the direction, all the direction.
I don't know if it will be good.
Perfect.
Good, good.
Then
Not
the
only you know a lot about eigenvalues and eigenvectors, as you are a wonderful sketcher. So what about the other vector?
1 -1.5, so something like this here. And now this one is associated with 1, so it goes to infinity, right?
Good, good, good.
And the other one is associated with lambda 2 -1, so it goes to 0. And for the other points, we have the combination.
It approaches. It does not go away. It approaches, no? Because this time is always vanishing,
Okay.
so it approaches.
Okay.
Okay.
Yes. So it will be something like this.
Good, good, very good. So Maxi will give the next lecture. And the one after that will be done by Cafe, and then Jose will do the.
Okay.
I will put
show
here
you.
a video of myself saying silly things while you give the lectures.
Okay.
Okay. So what is, if you compare now, we can go to, that's B. Okay. You agree?
Yes.
Let's project the. Let's project the plots. You have it, Maxi?
Yes.
If you don't have it, I have it. So you have to release the screen, and I will share it. So it's here. Okay, so this is one, and the other was here. You remember that it was eigenvalues at 1, 1, and minus and 1 minus 1. So 1 up and 1 down. Okay, and the one that Max did was this one. Okay, which is B. Good. Questions about this problem? Okay, so now I would like you to tell me what you know about Waterloo.
Waterloo
Waterloo.
is a city in Belgium. No, Belgium.
It's
or
not
Holland.
exactly a city, it's a village.
Oh, it's a village, okay.
It's a small village.
But it's in Belgium, no?
It's in Belgium, close to Brussels. And why do you know that?
It's because it's where Napoleon troops were defeated by the English
Okay.
in the around the first half of the 19th century.
The first half? No, longer
No?
than that. Much longer than that.
Okay.
Okay.
So then, okay.
1815. In the
Yeah,
summer.
but 1815 is in the first half of the 19th century. Is correct?
In the first half, okay, but not close to the half, close to the beginning.
Yeah, because I was not sure, so
So,
I knew it was before 1850.
okay, it's okay. What about Emaxian Cave? Do you know about the story of Waterloo?
No.
No, but you
And-
know who was Napoleon?
Yes.
Yeah, of course. Yeah.
So who was Napoleon?
Like
I can give you two answers. One, he had a very good restaurant close to Príncipe Real, and the other one, he was an hairdresser where my mother used to go. So two answers, two possible answers for this. Which one do you choose? Who was Napoleon Cafe? You know?
yeah, so maybe the restaurant,
The
but
restaurant.
yeah, but use I think the French.
He was an emperor of the French, and
French, yeah,
and he invaded the whole
yeah,
Europe, in
yeah,
Russia and Russia.
yeah, but he has been defeated by the Russian, yeah.
He has been
Yes.
defeated by the Russian winter. Okay.
Yeah,
Exactly,
exactly.
That's yeah. It's amazing that there were some people in the 20th century that didn't learn the lesson, and they were also defeated by the winter.
Oh, that's right.
Yeah.
That's
the
right.
winter Russians.
Yeah,
No.
exactly.
If people would read history books.
What do you know something about the battle? It was not exactly the British. The British were the most important part of the army
Yeah, it
that
was
confronted Napoleon, but there
I
was
just know the general. No, it was the Wellington.
Wellington.
General Wellington.
Wellington, the Duke of Wellington, who was in Portugal for 2 years, fighting the troops of Napoleon also.
Waterloo could also be an ABBA song.
Yes, that's right. That's right.
So yeah, could choose
Okay.
both.
Sometimes when I announce this problem, I used to tell my students to go and listen to the ABBA song
Okay, very good.
before. Okay, so but there was a coalition in the army of Wellington. They were speaking 17 languages, so you can imagine. And this was a very hard battle. More than 50,000 people died there. So it was a tremendous battle. And initially, the French outnumbered the Allies. So there were more French than Allies. And but before the end of the battle, and close to the end of the battle, there was another army, was from Prussia. Prussia is the northern part of Germany. And the general was called, you know what is the name of the general, Jose? Maybe you know.
The German one, but the only German, I don't know.
The
Bismarck, is that the only one? I
no,
know
no,
from
no,
Prussia?
much before Bismarck. It was one
I don't
century
know.
before. Blücher.
Okay, I don't know.
Okay, Blücher. And someone wrote that Wellington said, well, either the knight or Blücher must come, otherwise we are defeated. So Blücher came, and Blücher brought with him reinforcement and turned the side of the tide of the battle. So if Blücher hadn't come, probably the French would have won the battle.
That's another history lesson. The Germans always defeat the French.
Yes. But they win all the battles, in the end they lose all the war. Okay. Now, I want to model this and to use what we know about eigenvalues and eigenvectors to understand the Battle of Waterloo. Okay. So I have two armies, and how can I write a state model? How can I define a state to model this problem?
You have to. We start with two initial conditions, which is the Allied army.
So how many state variables? How many state variables?
I will say two because it's the
So you
two
have
first
x1
and x2, which will be
X1.
the armies.
and x2. Okay? And x1 is what?
It will be the French army, for example. No?
Okay, let's call it's the number of soldiers in the French army. I just put an F. And this is the number of soldiers in the Allied army. Okay? Now, I want to write two equations for x1 and x2. And I want to write these equations as simple as possible. So x1, this is the rate of change of the number of soldiers in the French army.
Should be x1 in times 0 minus.
I want the one thing is the initial condition. So this is just the rate of change. Okay, so.
Oh, so it's x1 through time.
Sorry?
If it's the change of, it should be dx1 divided by dt. No?
No, x1 dot is the rate of change. This is the derivative of x1 with respect to time.
Oh, okay.
How do you think the rate of change? The derivative is the rate of change.
Yeah.
So have you need an expression. You need an expression. Let's call it phi of x1, x2. That's the way we are writing the state models up to now. Okay. So I want to have something linear. So maybe a constant plus beta x1 plus gamma x2. And then higher powers, but let's think about this alpha, beta, and gamma. What do you think about this alpha? So could it be x1 dot equals to alpha plus something? What does it mean? Suppose that it was that beta and gamma were 0. So I would be x1 dot. If beta and gamma
it was
0,
alpha, it was alpha.
So you have x1, and now you have time. Okay, and you start here at x1 of 0. And then you say x1 dot equals to alpha. What is the evolution of x1?
It's always towards 0 with time.
Towards 0?
Of course, people will die.
Towards 0, why towards 0?
Okay, in this case, it's easy because soldiers will die. So
Okay, so you don't need the British. The British could go away and the French die for themselves.
so you also need the British. Okay, yeah, you're okay, yeah.
Okay, so to have
But nonetheless, if it's the sum of both, but nonetheless, it will always tend to zero, no? Because
I'm just trying to figure out whether alpha, beta, and gamma, what makes sense here. Okay, now consider just alpha. Alpha makes the French reduce. Without the British to do nothing, to the Allies, they do nothing, then the French, they reduce. Is this reasonable?
no,
Probably not. Or
No.
if alpha is
No.
positive, if alpha is
No.
positive, they grow. It's also not. I mean, you have a source of soldiers. No, so alpha should be, I would say, 0. Then we have beta. Then we have beta. What is the effect of beta? So beta x1. What does it mean? Beta
It
can be.
grows.
Sorry.
If beta is positive,
Mhm.
it will grow exponentially.
So if beta is positive, the x1 grows. What
Yes.
does it make sense? I mean, you
No.
have the army, and you do nothing, and the army is growing. What about if beta is negative?
It will decrease exponentially.
So this means what? I mean, in terms of something happening in the army,
They are dying.
they are dying by
Okay.
natural causes.
Yeah.
So by that's mortality rate. So let's assume that the diseases killed them in several days or several weeks. So the battle took about 10 hours or 11 hours. It started at 11 o'clock in the morning and went and stopped at sunset at 8:30 or something. So 9 to 10 hours. Okay, in 9 to 10 hours, the number of soldiers that died due to measles or influenza or some of tuberculosis, well, it's neglectable. So beta is again not here. Now you have this gamma. If the previous two are 0, maybe we can put gamma to 0 also. So our equation would become gamma. Now gamma x2. Now it depends on x2. What does it mean?
That the rate of the French dying depends on the ally army. Makes sense.
Okay, and should gamma be positive or negative?
Positive, negative. No,
Negative. Okay.
negative. Yeah.
Because the more allies there are, the more French die. So we end up with something which is minus some positive coefficient times x2. Let's suppose that the coefficient is just 1. Okay, I take gamma to be -1. Okay, so if you want, I'm normalizing things, or so -1 minus x2. Now, what about x2 dot? What is the equation?
It should
x2
be also
dot
minus x1.
minus x1. Very good. Now, you can write it as x1 dot, x2 dot in matrix form equals to 0. And here,
-1.
-1. Here,
-1.
-1.
0.
0. x1, x2. Okay? Now, I want to know what is the phase portrait of this. So I want to sketch my phase portrait. So x2, x1. So compute the eigenvalues and the eigenvectors. Do it. So what are the eigenvalues?
One and minus one.
1 and minus 1. So you need the eigenvectors. Go ahead with the eigenvectors. So B1 is what? And B2 is what?
Would be like 1 over 1,
1, 1,
1, 1, and 1 minus 1.
1, 1. As I said, if you don't learn anything else, you will learn how to compute eigenvalues and eigenvectors. So what is the phase portrait?
So
The first thing that I should do is do what? Plot what?
The vectors.
The eigenvectors, no?
yeah,
So
eigenvector.
one is 1, 1, something like this. So it's this direction, no? Okay. The negative part is useful because it gives you the idea, although we only use the positive one. And the other is 1 minus 1, so it's something like this. Now, along this eigenvector 1, 1, where do I go? If I'm here, where do I go?
To the outside. No?
But this is incorrect. It's not changed. This is the eigenvector corresponding to minus 1. So let's do it like this. Or okay, so you should be careful. So here you go
Out
to the origin.
inside. To
Okay.
the,
And here you go where?
outside.
Outside. And here you go outside. Now, if you are here, where do you go? If you start here, where do you go? It's the composition of the two movements, no?
Yeah.
So you approach the origin and you do something like this, and then you continue. If you start here, what you do?
You go down
You go
to the
down.
origin, and then you start to go outwards.
Something like this, okay? You agree?
Yes.
Now, the French, initially, they outnumbered the Allies. So let's suppose that we have x at time 0 is equal to 3-2, okay? Now, you don't fight a battle with 3 soldiers, but you can fight a battle with 30,000 soldiers. So imagine that you multiply everything by 10,000. Actually, it was 60,000 and 50,000, okay? But let's assume that one here represents 10,000. So you are here, and according to your model, who wins the battle? So you start here at this point, which is 3-2. Who won the battle?
Who won the battle?
Who won the battle? Quem ganhou a batalha? Waterloo, de acordo com este modelo. According to this model, you start here.
France,
Yeah.
Who?
the French soldiers,
Why?
because initially it is decreasing, but then the number of
You
Oh,
end up
wait.
in a situation where what happens?
But there x2 is 0.
X2 is 0. No more allies. No, you exterminated the allies, and you still have some French. Okay. If you start with an equal number of troops in both sides, what happens?
Both all die.
Everybody dies.
Yeah.
Okay. So
Everybody
this
dies.
shows how this model at least shows how stupid it is to battles and wars and this stuff. Okay. No, but you know that the British won the battle. And what are we forgetting? Blücher, my friends, Blücher brought the Prussians. The Prussians came. So there was a moment in which the Prussians came. So suppose that your state is evolving. At some time you are here. Okay. And when the Prussians came, what happens to this? What happens to this diagram? The Prussians bring a reinforcement of the Allied army.
it goes up.
So you do a change up. And then what happens?
Yeah, the French go to 0 while the x2
You
go
now
up.
follow this line, okay?
Yeah.
So you change this initial condition, and you now follow this line, and Wellington won. Okay? So you can interpret this with eigenvalues and eigenvectors.
Actually,
No.
that was a really nice way to show it.
Okay, so we explain history. Now, Café, at least, if nothing more, you learned about Napoleon and Waterloo. Do you know the ABBA music? You know the ABBA? You
No,
don't know
I don't
ABBA?
know ABBA. No.
This does not pass in Iran, I guess. But,
Yeah, of course.
okay, but apart from ABBA, Napoleon is a serious guy. He had interest in the East, but
He didn't have a time. He didn't have a time for that.
He had not time to go there to spread his light.
Yeah.
Okay, his armies came to Portugal. Okay, and they were killing and burning and destroying everything. So now there is still one problem, which is the despair of Wellington, because Blücher was not coming. If Blücher came too late, what happens? Or in other words, what is the latest time for which Blücher could come and still turn the battle to the other side?
What was the time?
It is near to.
Is there a time limit? Before answering what is the time limit in terms of this diagram?
Until it will reach to the x1 level, so it is like,
Until it reached what? So it should be
yeah,
here.
Yeah, here. Yeah.
The time limit is such that is here and it brings something, and this should be, what is the condition?
X2 should be
In
bigger than
geometrical
0.
terms. So x2 should be bigger than 0.
Yes.
Yeah.
For instance, if he comes here, would it work? Suppose that
Probably.
it has this amount of soldier. What happens? I still have, say, 2% of the army there, and then Blucher comes, and what happens then? He comes to this position.
No, again it will decrease. So
Again, it would be something
Yeah.
like this.
Yeah, decrease and die. Yeah.
Okay. So what is the limit? What is the limit?
So it must be above. So it must be.
It must be what? Above what?
Yeah. So it is like the green point. So it is
The
like,
green point, and you
Yeah.
jump, and where should you go?
so upper than the x2 level. So it
This
will
is
then
this is the limit. This is
Yeah.
the limit. Okay. Now, let's do some computations using another color, blue. So, what do you have? This blue line is equal to this blue line, but this blue line is the number of x1 at time. Let's call it TS. Okay. So x1 of TS must be equal to what? Must be equal to this small part here, which is x2 of TS, plus the reinforcement, let's call it's 2. Suppose that the reinforcement is of 2 soldiers. Okay? Suppose that he was bringing the amplitude of the army of Blucher, the red line or the green line, it's 2. Okay? And this is the condition for TS. Now, how can we compute TS from this? We need expressions for x1 and x2. What we know. Can I erase this stuff here? Also this stuff here. What we know that x1 of t and x2 of t. What is the expression of the solution of the equation? What is the expression? It's k1. What? And then the story of the model decomposition, it's times the eigenvalue number 1. Sorry, the eigenvector number 1, 1 minus 1, exponential of t plus k2, 1 exponential of minus t. Okay. Now we need to know k1 and k2, so we know the initial conditions 3, 2. So 3, 2 equals to k1, 1 minus 1, plus K2, 1, 1. Okay, so 3 equals to K1 plus K2, and 2 equals to minus K1 plus K2. So 2K2 equals to 5, and K2 equals to 5 divided by 2. Okay, and K1 is equal to say 3 minus 5 divided by 2 from the first equation. So should be 15 minus 5 divided by 2, which is 5. Just let me check my notes. There is...
It should be 6 divided by 2. So
Yeah,
6
6.
Yeah,
It
minus
would be
obviously
like
that.
3. Yeah, it would be like 3. Yeah.
1, 1, 1, 1. 1 minus 1, T. And so here it's K1, 1, 1, K2, 1, 1. So if you add these two, you get 5, and you get 2K2. So this is correct, 2.5.
Yeah, but the K1,
K1.
should be 1/2.
Yeah, like
Should be 1/2.
0.1.
1/2.
Yeah, yeah.
And this is 2.5. Okay. So I put here K1. K1 is 0.5. And I put here 2.5. Okay. And this was obtained by applying the initial condition. This initial condition, 3, 2. Okay. Now I've canceled things too much because, okay, x1 of t is 0.5 exponential of t plus 2.5 exponential of minus t, and x2 minus 0.5 exponential of t plus 2.5 exponential of minus t. Okay. Now our condition was x1 of ts. Now the condition for this specific point, is equal to x2 of ts plus 2. So x1 of ts is that stuff here, 0.5 e exponential of ts plus 2.5 exponential of minus ts is equal to minus 0.5 exponential of t plus 2.5 exponential of minus t plus 2. Now, this term cuts with that term, and these two terms just give you exponential of ts equals to 2. That is to say, ts equals to log of 2, which is 0.67, okay? If you take the time in 10 hours, so 1 unit of time is 10 hours, that gives you, say, 7 hours, 6.7 hours, okay? And the battle took about 9 hours, and Wellington, and actually came. So this does not mean anything, but it's not a silly estimate, because it came at 8 o'clock in the evening, so close to 9 hours of the battle, and our estimate is 0.7 hours, the limit. Okay. So this example shows how you can pick up a problem, and Waterloo speaks about your own problems of your PhD activities, and write a simple model and then take some conclusions. Okay, not all the problems can be solved with linear models, but sometimes you can have a first idea, and using these concepts is a useful thing. Any question?
Mm.
I hope you enjoyed my explanation of the Waterloo battle.
Yeah,
So
thank you for explanation.
we'll see each other
Wednesday.
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 Yeah, thank you so much.
Thank you so
Okay,
much.
so have a nice evening. See you.
Yeah,
Bye.
you too. Have a good night.
Bye-bye.
Bye bye.